Greetings and welcome, friends. Mr. Waddy here. We're taking a look at 7.4, talking about solving. Okay, solving. When we solve, we did what? We isolated a variable. We found out what numbers made an equation true. So we're solving polynomial equations. Polynomial equations might not be linear like the ones we've dealt with before. There might be squares or cubes or different things like that. And these polynomial equations are in what's called factored form. And we're going to define that for you right now. So here we go. It says, using the zero product property. That's the big idea today. I'll show you what that is in a moment. But first, some definitions. A polynomial is in factored form when it is written as a product of factors. Okay, a product of factors. And these factors have a highest degree of, well, no, never mind. That might not be the case. No, we'll just leave it at that. Product of factors. All right, we'll talk about kind of fully factored later on in this, this chapter. Okay, so standard form of a polynomial was when we wrote it from highest exponent to lowest. Remember, we went kind of downhill with exponents. So here's 2, here's 1, you could technically see an x to the 0 there. 2, 1, 0, right? It's going down. Actually, I think I sang that going higher and higher. So I'd need 2, 1, 0. I don't know, is that better? Sure. Okay, the factored form of this is if I write it as the product of things. The product of things. All right, and usually those things will be, for us, they're going to be linear or first-degree polynomials. They could be binomials like here. It could be a monomial times a binomial, things like that. But these are called factored when it's written as a product. All right, kind of like, you might remember writing the number 12 in its prime factorization, right? Which, right, you'd kind of make the factor tree. Do you guys remember this? Right? Which I don't actually see these as a tree. I kind of see this more like these are potatoes growing underground. But that's fine. So the prime factorization of 12 was 2 times 2, which is 2 squared, times 3. So factored form, think of it as it always is going to be a product, just like when we had prime factorization. Okay? All right, now here's some interesting stuff. When one side of an equation is a polynomial in this factored form, so it's written as a product, and the other side is 0, use the zero product property to solve the polynomial equation. All right, we'll see what that is in just a moment. And then it has this interesting thing. It says the solutions of a polynomial equation are also called roots. So roots means solutions. All right, these are synonymous when it comes to polynomial equation. So I could say, what are your solutions? What are your roots? All right, same thing. So what is this zero product property? What is it? Let's find out. The zero product property. And we were just talking about some properties of 0 and 1 just before this lesson, me and my friends in real life here. And the zero product property says this, according to words. If the product of two real numbers is 0, then at least one of the numbers is 0. So, okay, all right. Or it says it this way mathematically. If a and b are real numbers, and a times b equals 0, then a equals 0 or b equals 0. Must be one of them, at least, right? At least. Could be both of them. Could be both of them, right? The only things that multiply to be 0, there's got to be a 0 involved somewhere, right? So how do I use that to solve an equation? Let me combine some of these thoughts for us in example 1. All right, so check this out. Here's example 1, part A. Is this factored? Okay, it's written as the product. Yes, so it's factored. And it says solve each equation, and we were just told we could use this zero product property to solve our equations. And notice what I've got here. I have two things multiply to be 0, right? Just like the zero product property. Two things multiply to be 0. Therefore, right? There are two possible outcomes here. Either this 2x was equal to 0, or x minus 4 was equal to 0. And it's even possible that both of them were 0 at the same time. So I'm going to write this. So based on this, based on the zero product property, either 2x equals 0 or x minus 4 equals 0. So I'm breaking this up into two cases, just like when we were solving absolute value equations back in the day. You broke it up. Break it up. And I'm using the zero product property to do that. So now let's just solve both of these. And that'll be like good old times. Solving equations using inverse operations. All right, there we go. So I get x equals 0 as one of the possible solutions or roots. Roots! Hooray! And the other possible solution, if I add 4 to both sides, is x equals, 4. Right? Yep. So I get two solutions. Sometimes there will be more, okay? But this is the idea. If two things multiply to be 0, one of them had to be 0, and then I just solve for both of those possibilities. And now I've got two solutions. So here, how about this? This is in factored form because it's written as the product of two things or more things. Two things multiply to be 0, so therefore one of them must be 0. You got it. All right, so let's break this up into two cases. Either x minus 3 equals 0 or x minus 9 equals 0. Two cases. Now, this is actually a super illegal way to think about this. Well, it's got to be 1 because, right, if I told you 3 times some number b was equal to 0, you would say b has to be 0 because the only way I can multiply things to be 0, right? One of them had to be 0. That was the idea. Both of them are. They're just not both 0 at the same time. It's going to be weird. We'll get used to it. But here's a weird idea that might help us. Remember distributive property? The idea that I can distribute multiplication over addition, or I can distribute exponents over multiplication. It turns out equality of 0 can be distributed over multiplication. This is a super illegal way to think about it. But notice that is kind of what's happening. Right? I get x minus 3 equals 0, or x minus 9 equals 0. All right? So you could kind of think about it that way. But that is absolutely the wrong use of the term distribution. But I like to sometimes think of things illegally like that if it helps me remember what I'm doing. Yeah, it worked out. So let's see, to solve these, I'm just doing that simultaneously. I get x equals 3 or x equals 9. Now, it's not both of those things at the same time, but both of those are solutions or roots of this equation. What's up? I'm not saying that x was equal to 0. I'm saying that this was equal to 0. And watch, let's actually do a check. That's actually a great idea. So if I do a check, let's plug 3 in this original equation. So I'd have 3 minus 3 times 3 minus 9. Is that equal to 0? What is 3 minus 3? That's the 0. So I was saying that this entire thing was equal to 0, not that x was necessarily equal to 0. X was just whatever number it took to make this set of parentheses equal to 0. And let's see, 0 times negative 6 is in fact 0. So that does work out. Good. That's a really good question. Thank you for asking that. And then let's plug in 9. So 9 minus 3 times 9 minus 9, is that equal to 0? 9 minus 3 is 6 times, what's 9 minus 9? 0. So that's where the zeros are showing up, and 6 times 0 is 0. Okay, so yeah. Oh wow, man, that actually just made that lesson so much better. The fact that you asked that. Thank you. All right. So let's do a couple more of these. I'm gonna solve some equations when my polynomials are in factored form. All right, actually, let's have you guys try this one, and I'm going to skip 2, and we'll try, so let's try 1 and 3. And for my internet friends, you guys can just hang out for a minute, as I'm going to walk around and check on my students as they're doing this. Feel free to put some music on, and then the next time you see my cursor move, you'll know I'm back. Let's see, Mr. Waddy's back here. So let's break it up. Break it up. Yeah, you can do the other one. I'm just going to catch up to what you guys did on problem 1 here. So either x equals 0 or x minus 1 equals 0. This one's already solved conveniently. And then this one I add 1 to both sides. So I get x equals 1. So 2 solutions, 2 roots, right? And over here I'd have z minus 4 equals 0 or z minus 6 equals 0. Right? Just break it up, the idea. Add 4 to both sides over here. Two solutions. 2 solutions. Okay. Good. Let's see, another terminology. Now, so far, both of our solutions have been different from one another. But it is possible that you could have the same solution show up twice. It's possible I could have both like 1 and 1 show up. And when that happens, an equation has the same roots. It's said to have repeated roots. Like, 2 numbers that add to be 0? Is that what you're saying? That I don't know. They could actually be anything. Like if 2 numbers, this is actually an interesting side concept. If I have a plus b equals 0, it's possible that a could have been 10 and b could have been negative 10. That a could have been 72 and b could have been negative 72. Let's see, for 2, oh, what was it? Let me see. Let's see, for that one, I would have just broken it up into 3t equals 0 or t plus 2 equals 0. I break it up over the multiplication part. Okay? All right. So let's see. Let's take a look at example 2. Example 2. It's going to have repeated roots. So, here we go. Break it up. Here we go. I'm going to break this up into 2 cases. And this one, I'll break up into 2. Actually, I'll write this again. So let's see. So either 2x plus 7 equals 0 or 2x minus 7 equals 0. Hey, wait a minute. Guys, remember, wait. Huh? These are almost the same. They're almost opposite. It's already factored for us, but I just want to point out that we do know the pattern to multiply those. But in this case, I don't want to multiply them because I like the fact that they're already like written in their factors. But I just wanted to point out that the pattern would have applied if I multiplied those out. Yeah, I got to get x by itself using inverse operation, so subtract 7 from both sides, so 2x equals negative 7. And then what do? I divide both sides by 2. Yeah, I'll just leave that as negative 7 halves, a reduced improper fraction. Unless it was like a word problem, then I would, have... So I'd have... And then divide both sides by 2. Yeah. Just x equals 7 halves. Now, these weren't the same number. These were opposites. So these are not repeated roots, like I mentioned up here. But I just want to point out, even when there was like a number in front of the x, or these were a little bit more complicated, the idea was I've got the product of two numbers equaling 0, these big numbers, whatever they are, and I just break it up into two cases. Either the first number was 0 or the second number was 0. Now, x minus 1 all squared, I'm just going to write this down as x minus 1 times x minus 1. Because that is what squaring means, right? To multiply something by itself. And if I break this into two cases, these are going to be oddly similar to one another. Yeah. So if I add 1 to both sides, I'm going to end up with x equals 1 or x equals 1. This is a situation where I have repeated roots like they were talking about a moment ago. All right, so repeated roots are when the same solution shows up twice or more than twice. It is possible. These will have implications on the graph of a polynomial later on in the future. Maybe Algebra 2, you'll recognize some of those patterns. But right now, you don't have to worry too much about that. All right, how about, whoa, what? C? What? Not quite. Here, let's see. I'm actually going to snapshot this and give myself some more space. I'm going to write it down here. Let's see. Sorry. Yeah. So I'm going to, all right, if 3 things multiply to be 0, do you think one of them had to be 0 still? No. One of them's got to be 0. One of them. So either x plus 1 was equal to 0, x minus 3 would have equaled 0, or x minus 2 was equal to 0. One of those equations has to be true. So like zero product property doesn't just only work when I have 2 things that multiply to be 0, right? I could have had like, if a times b times c equals 0, then either a is 0 or b is 0 or c is 0, right? One of these things equals 0, but it's the same idea. I break it up, and now I'm going to just solve each of these. Here I would have subtracted 1. I'm just going to, well, I've got my color out. No. X equals negative 1. Yep. Nope, just negative 1. Why do I have a half? No, there's no number in front of the x. Right? That we only divided when when there was a 2 in front of the x. So let's see, x minus 3 equals 0. To get x by itself, you would add 3 to both sides. So I get x equals 3. And x minus 2 equals 0. The inverse of subtracting 2 is adding 2. And so I get 3 solutions here. None of them were repeated roots, but that's okay. They don't need to be. They don't need to be. All right. Now, we've given you problems where these were already factored. And the rest of this chapter, I'm going to help you get things into factored form so that you can use this zero product property. And the first way we're going to talk about factoring is using the GCF, greatest common factor. All right, GCF, greatest common factor, which will allow me to write a polynomial as the product of, right, these things. and then I could use the zero product property, because not all the time will it conveniently have just been given to me as a factored polynomial. And so greatest common factor, it says to solve a polynomial equation using zero product property, you may need to factor the polynomial or write it as the product of other polynomials. Look for the greatest common factor of the terms of the polynomial. This, what is the greatest common factor, is a monomial that divides evenly into each term. So here we go. Here's example 3. It says factor out the greatest common monomial. What's monomial mean again? Yeah, you don't have example 3? Flip the page. Yeah, it's got to be there. Bam. Got it. All right. So factor out the greatest common monomial factor. What does monomial mean? A single term from these two things. Greatest common factor, I call undistribution. All right? Right? The distributive property was when I would take, here, I'll make a little side note, right? If I had A times B plus C, right? The distributive property was when I would go roop, 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 and like multiply A into that. What I'm doing now is undistributing. I'm what I sometimes say, like when Homer Simpson steals a donut, you just go a yoink, right? I'm stealing something from each of these terms. All right, a yoink is what we're doing. And the thing that I steal has to be common. I have to steal the same thing from everybody. All right? Well, let's show you how this works. So to find a common factor that I could steal from these, let's look just at their coefficients first. So between the number 4 and the number 24, what is a common factor? What is a number that goes into both of those? 4. All right, and that's the greatest common factor too, right? 2 goes into both of those, but it's not as big as 4. So I'm going to steal a 4 from each of these. 8 goes into 24, but 8 can't fit into 4, right? It has to divide evenly into each term. So, right, so that's the sort of thing that we kind of keep trying until we figure it out. And now I've got an x to the 4th and an x cubed, and it turns out when it comes to variables, I can steal the variable with the smallest exponent, right? Because x to the 4th, I want to point out, is going to be the same as x cubed times x. Well, we'll see what happens. We'll see. Let me get there. Let me get there. So if I steal this number from both of those, right, and I'm undistributing, so I'm going to write this number on the outside of a set of parentheses. And so 4x cubed times what, right, what number would go here, would have given me 4x to the 4th. Well, 4 times 1 would give me 4. So it's got a coefficient of 1. Right? What's going on here? My laptop's going crazy over here on my second screen. All right, so 4 times 1 is 4, and x cubed times what would be x to the 4th? X to the 1st, right? Because 3 plus 1 is 4. That's what I'd written up here, right? X cubed times x to the 1st is x to the 4. Whoa, what is going on? My computer keeps like alt-tabbing on me. Sorry, what's your question? Well, let's find out. So let's see, 4 times what would go here? 4 times what would have been 24? Or to ask it in the other way, 24 divided by 4 is 6, right? And it's positive 6. And x cubed times what would have been x cubed? Well, that's just 1, and so I don't even have to write that. So the factored form of this would have been 4x cubed times just plain old x plus 6. So I'm stealing, right, the biggest thing I can that everybody has. So it's like if you had a flat tax rate and you were like the king of some kingdom, you can only tax what the poorest person can afford to give, right? As you're like going around and saying, hey, yoink, right? And just, right. Right. Obviously, yeah, taxes are different depending on your income. But in this case, with greatest common factors, we're stealing the same thing from everybody. So let's see. Let's look at this example. I'm going to do this faster, okay? So what number goes into 8 and 24? In this case, that the biggest number is 8. And y squared and y to the first, I could steal one y from each of those, right? I could steal a y to the first from each of those. So I'll have 8y times, 8y times what would have given me 8y squared? No, 8 times 1 is 8. And y times y would give me y squared. And 8y times what would have given me negative 24y? So 8 times a negative number would give me negative 24. No. 8 times what is 24? Or ask it in reverse. 24 divided by 8 is what? 3. And y times what is y? Well, that would have just been 1. Y times 1 is y. So I don't even have to write that. So my factored form is 8y times y minus 3. All right, so let's combine these skills. Let's combine GCF, greatest common factor, and the zero product property. This is a big deal, big lesson today. All right, so example 4. I'll walk us through this. So, first of all, this is set equal to 0. I like that. Because zero product property only works when it's equal to 0. Now, this is not factored. So I'm going to attempt to factor it using GCF, which doesn't always work, all right? But conveniently, we're giving you problems today where they are factorable, okay? The book was kind of nice like that. So what could I steal from both of those? Between 2 and 8, what's the biggest number that goes? Is 2. And between x squared and x, I can only steal what the poorest person can afford. So that's x. So 2x is what I'm stealing. So I'll have 2x times something in parentheses equals 0. 2x times what would have given me the 2x squared? No? Yep, 1x. 2x times x is 2x squared. And 2x times what would have been 8x? Yeah, plus 4. Yep, 2 times 4 is 8, and x times 1 is x. And now that I've factored it, hey, check this out, the zero product property applies. So we're combining both of our skills, right? Just like in a video game, our first little bad guy we fought was zero product property, and then the second one was factoring with GCF. And now at the end of the level, we get to a boss where we have to use both of our skills simultaneously. You know what I'm talking about. You know what's up. So 2x equals 0, or x plus 4 equals 0. And so to solve this, how do I get x by itself on this side? Yeah, it's being multiplied by 2, so to undo that, I divide both sides by 2. Correct. Let's see, let's have someone else walk me through this other one. How do I get x by itself over here? Minus 4, because the inverse operation of adding is subtracting. And so I'm going to get x equals 0 or x equals negative 4. And what's cool is if I plug, I'll do a check just for the negative 4 one, but you could check 0 as well. If I plug negative 4 into both of the x's in the original problem, negative 4 is going to work. And we will have just solved our first polynomial equation that we had to factor ourselves. So let's see, 2 times negative 4 all squared plus 8 times negative 4. Is that equal to 0? Let's find out. Negative 4 all squared is positive 16 plus 8 times negative 4 is negative 32. So I'll write that as minus 32. And 2 times 16 is 32, and 32 minus 32 equals 0. Guys, we just found a solution of this crazy-looking equation, right? Like, if I asked you to guess the number of x that would have made that true, that would have been a very hard thing to do, but using these two skills, we were able to break it down. And also, it works if you plug in 0, and that's a little bit more obvious, but I'm not worried about that right now. Let's look at part B. All right, last example, because, yeah, we're running out of time. I want to make sure you guys get some questing time in here. I'm going to rewrite this. 6n squared equals 15n. I just want to give myself a little bit more space. Now, in order to use zero product property, right, my end game is using the ZPP. In order to use ZPP, it's got to equal 0, which it is not currently equal to 0. So I'm going to move this 15n by subtracting it from both sides. So what I'm doing is it's like I'm solving for 0. If you want, so 6n squared minus 15n equals 0. Let's actually write down in our notes why we're doing this. All right, so I'm solving for 0, so to speak, for 0, comma, so ZPP will apply, right? So ZPP will work later. That's what I'm trying to do, all right? So I'm getting everything away from one side of the equation so that it's equal to 0. And now it's equal to 0, but the question is what's on this side of it factored? Is it written as a product? No, it's not written as two things being multiplied. And right now, the only way we know how to factor is to yoink, right? GCF. So what could I steal from 6 and 15? What's the biggest number? 6 doesn't fit into 15 evenly for division. 2 doesn't. 5 doesn't go into 6 evenly for division. 3, there we go. And between n squared and n to the first, the most, right, that I could steal from both is n to the first, because this one, that's all he's got. That's all he's got. So let's see. So let's write this. So 3n outside a set of parentheses equals 0, because I'm undistributing. That's what factoring is. So 3n times what would equal 6n squared? 3 times what is 6? There's going to be an n in it, because n times n is n squared. And 3 times what is 6? 2. Yeah. Right? Or I can ask it backwards. 6 divided by 3 is 2. All right. 3 times what is negative 15? It's going to be negative. So 3 times what is 15? Yep. And this one's already got the n, so I don't need any more n's here. Right? So 3n times negative 5 would give me negative 15n. And now to solve, now guys, I just want to point out, sometimes students will be like, oh, now I distribute, which is, we just undistributed. So don't do that. Now I want to use zero product property, so I'm going to break this up. So 3n equals 0, or 2n minus 5 equals 0. And I'll solve this real quick. Divide both sides by 3. Yep. And over here, we'll add 5 to both sides. We're going to get a fraction. That's fine. We're fine with fractions. So 2n equals 5, and then divide both sides by 2. All right. Today's lesson is a big deal. Yeah, so 5/2 or 2.5. All right, let's call it on this. Thanks for watching, internet friends. Bye-bye.